So welcome back everyone. Hope you guys had a great lunch. Hope you guys are not sleepy. Even if you're sleepy, I think we have a bunch of electrifying talks for this session and the next that's going to wake you up. Yeah. So the first speaker for this session is Pradeep Ramachandran, who is the director and head of research at KLA's AI and Advanced Computing Lab in the IIT Madras Research Park, and he works on taking semiconductor manufacturing to the angstrom scale that he'll talk to us more about today. So he completed his bachelor's at IIT Madras and his master's and PhD from IISc. And his work has been around building systems that bridge hardware and software. So you're going to see a systems-rich talk that a lot of people were cribbing about yesterday that they lacked seeing, right? But what I found super interesting while reading his bio is that when he's not tackling these, nanometer-sized problems, he actually has a much larger problem to tackle, and that is matching the energy of a 6-year-old son. He said he loves rolling on the floor with his 6-year-old son, right? And all that reminded me was I have a nearly 2-year-old who does the same, but he does that crying on the floor. And when I read that, it just helped me feel good about life, thinking there's light at the end of the tunnel for all those PhD students who are struggling currently, right? So with that, I'll let Pradeep take over.
All right. Thank you very much for the warm welcome. I do try to match my son's energy. I'm not going to roll on the floor here, but I'll try to keep this entertaining. So it's always challenging to do the first talk after lunch, especially we have lunch standing up. You sit down, it's a cool afternoon, AC kicks in, serotonin kicks in. So what I'm going to do is I'm going to make you all do an exercise. So humor me, everybody please stand up. Just me, it's worth it, please. I'm not going to make you jump or something. Please stand up, just open up, please stand up. Let's do a quick exercise, right? So I'm telling you that we use AI to do semiconductor manufacturing in angstrom scale. Let's just take a poll right now. If anybody has used AI today, sit down. Okay? 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 Some of you have not used it today. Okay? If anybody used AI this week, sit down. Who's sitting? Just give me a second. Okay? If anybody has used AI this month, please sit down. Okay, wonderful. Okay, hopefully you all got your energy together now. So let's talk a little bit about how AI, which obviously all of your lives in the last month has influenced, we use it to actually do angstrom scale manufacturing. So before I get started, I'm delighted to present in front of my academic grandfather. I'm Sarita student from University of Illinois, and thanks Arka for putting together what in my opinion is one of the best workshops I've attended in a long time. Fantastic talks, thanks to all the speakers, and I'm delighted to be on the stage. So what I thought I'd do today really is to spend most of my time giving you a background. Right? It's ironic that I don't want to talk about what work we do. I will still do that, but I feel that this world of semiconductor manufacturing is not understood enough. In fact, I joined KLA in 2021 to start the Advanced Computing Labs. I've been a chip designer for a long time. I've built software. I was responsible until the GDS2 was given out to the fab. I'd get back silicon, it wouldn't work, and I would crib saying they don't know how to manufacture. Right? So now what I'll actually do after that is I started to understand when I started the lab what manufacturing actually does. And it is a fascinating one. So I'll spend the first 15 odd minutes talking about semiconductor manufacturing, how it actually happens, what we do with it. Then we'll talk about how we leverage both AI and HPC in manufacturing. Okay? So let's get going. And then I'll also talk about what's called process control, which is what we actually do. So let's first set definitions together, right? Taxonomy, extremely important. What is a chip? We all think about a chip as this, right? But that's not really a chip. It's actually a chip on a package. These individual elements that are packaged together is actually what is this. This is a chip on a package. A chip is actually this little piece, right? Just for physical sizes, a typical NVIDIA H100 chip is a little bit larger than the nail in my bigger thumb. That's as small as it is, and it powers and costs whatever $30,000. Pretty incredible, but that's all it is. So a chip is actually this, and the way that chips get manufactured is actually on wafers. So silicon wafer is typically a 300 millimeters, about 8 big. It's a circular disc that is really made from sand. Right? You've seen all the Intel ads that say sand to silicon. It's actually true. They take sand, put it in a large furnace, they melt it, and from molten sand, you spin it, it becomes a circle. That's where you get circular discs, and then you cut it, and you get silicon wafers. So chip manufacturing happens in silicon wafers, and we talk about how from a silicon wafer you end up with those chips and into the package. So this is the pipeline of actually how a chip gets manufactured. You start with, on the left side, what are called unpatterned wafers, which as I said, you take this big ingot of silicon, cut it. You get these unpatterned wafers that have nothing on it. It's just naked bare silicon. Why silicon? Because for those of you who remember from high school physics, silicon by 16 valencies has the most regular structure to form a lattice. That's why silicon is used. And of course, it's abundant sand, right? Your circuits that all of us have designed in our electrical engineering classes, all you circuit designers who design circuits, get converted into these reticles, which are, think of it like the negative of a photon. You want to draw a circuit, get the negative. For those of you who remember photography, that I haven't done photography that way either, but I've seen negatives of films, and then you get a reticle. The reticle is a negative of the circuit you want to draw. What then happens is a process happens by which you first deposit a photosensitive material on top of this wafer. Then you place the reticle on top, and then you shine light. Because the areas of the photosensitive material that's exposed gets an imprint of the circuit that you're trying to draw. Then you remove the reticle, you clean it, and then you take laser and you cut it. It actually is a laser that you cut with. And what happens when you try to cut something? Debris falls out. So then you have to clean it. CMP step is a chemical and mechanical polish where you pour chemicals to clean it, and there's a big grinder that actually comes and cleans the silicon. It really is a big grinder that comes and cleans. You wonder, okay, we're talking about this size, what happens there? We come there, right? And this happens for one layer. A typical chip today has anywhere between 150 to 600 layers. And every single layer goes through this process. It takes anywhere between 3 to 6 months for a chip to start from an unpatterned wafer to be able to come out of this process and for you to be able to electrically test it. And in that 3 to 6 months, in all that 150 to 600 layers, if you made one mistake, you got one wrong circuit drawn, you got one dust particle, every chip in every wafer that you made in that 6 months is not going to work. Right? And this happens in factories which is 2 to 3 kilometers long, which are about 10,000 times cleaner than an operating theater. Like, take a second to digest that. 2 to 3 kilometers, 10,000 times cleaner than an operating theater. So it's a really, really intricate manufacturing process. So this actually shows a cartoon representation of how the chip is actually grown. So this is a FinFET transistor, and it's cartoon, but it really, this is what happens. And this is, remember, the width I'm talking about from this end to that end is about 25 nanometers. And it helps me get physical relevance. The cross section of your hair is 10,000 nanometers. The cross section of this thing is 25 nanometers. And we're doing all this growth and cut and stuff. It's fascinating that it actually works at the end of it. And the complexity is increasingly becoming more difficult to manage because every device that you're manufacturing, whether it be a gate-all-around transistor, this is the transistor that's used for the 3 nanometer process that today is used on the M5 silicon that powers the Macs of today. The gate-all-around transistor is like a skyscraper. Those of us who study transistors in school, high school or college, you had a source, a drain, and something in the middle. Those days are over, way past. Right? A transistor today looks like this. Right? There's gate all around, complexities are very high. This is a cartoon representation of what 3D NAND looks like. The flash memory, your NVMe storage that enables all your AI, all the storage on your phones. The fundamental building block is the 3D NAND. It's hard enough to draw it in a cartoon. Imagine drawing this with the cross section being about 100 nanometers. It's really, really difficult. These reticles are also a very interesting problem because for those of you who remember your physics, when light passes through a surface, when light passes through a hole that's proportional to lambda, then we remember what happens. Light bends. Light bends and light disperses. So it's not as simple as making a reticle, right? You've got to pass light and the light is going to bend and go and edge some other way. So you've got to figure out how to make a reticle that gives you the impression that you want. It's a very difficult problem to solve. And if your reticle has one defect, every time you've printed every chip on every wafer has the same defect. You cannot afford to make a mistake. So chip manufacturing is actually a very complicated process. And in addition to manufacturing itself being complicated, the other thing that also happens is that in time, the same manufacturing factory goes through what's called a yield ramp. Like for example, when you move from say a 5 nanometer process to a 3 nanometer process, yield is currently initially at like 25%. What does that mean? If a wafer has 100 chips, only 25 chips work. But you have spent $30 billion setting up that fab. $30 billion is the typical cost of a 3 nanometer fab today. You sell a chip for $100. If I have to throw out 75 chips that I make, I'm not going to be able to do that. So the goal really for the factory is to start from a low yield and try and ramp it up to a high yield as fast as possible. So in time also, manufacturing is getting more complicated because initially you have a lot more defects, there's a lot more defectivity. Your tools are not perfect because your design rules are different. Those of you who have done chip design, remember design rules, right? Those design rules directly matter because suddenly in the new process, design rules are different. The reticles that you used in the previous process will not work now. You need new reticles, you need new ways to bend light. How do you do all that? So what KLA does is we provide equipment, which we call tools, which help you inspect the wafer at any intermediate stage of manufacturing well before you can electrically test it. So it's a machine. We have machines that are size of half of this room, larger. I think we have a machine about 3/4 the size of this room. These typically go into factories that are manufacturing semiconductors, and what they do is they take an image of a chip that's being manufactured. We try to find, is there a deviation from the design? Sounds like a simple problem because you have a design, you have an image, you have a design that's supposed to be, let's do A minus B, you're done is what you think. Hold the thought, we'll come back to that in a bit. So these are the kind of defects I'm trying to find, right? So here's an example. Try to draw two lines. Just remember, right, this is a circuit. And we all draw circuits with straight lines and scales. Doesn't look like scales anymore. There's no straight lines anymore when you manufacture. I'll show you a real manufacturing, what a real manufacturing chip looks like. But what we're trying to find is we're trying to find defects, which are deviations or outliers. We're really looking at the 5 sigma, 6 sigma outliers with respect to manufacturing. In addition, what we also do is with light, we do what's called metrology. So for those of you again who remember your transistors, there's a notion of a critical dimension. I was just talking to Mark about the importance of the nanometer number. Earlier it was very simple. Your dimension, the critical dimension was the distance between the source and the drain. So 22 nanometers at 22 nanometer distance, 16 nanometer, 16 nanometer. Today's transistors look nothing like that. So the 3 nanometer, there's not a single dimension here that's 3 nanometers, by the way. Okay, some loose approximation of what 3 nanometers is. But every single one of these yellow measurements that are shown here are critical. Any one measurement that is off spec, the chip will not work. Or chip will not function at the frequency that you wanted to. And all the work that we did to do performance modeling, that do performance simulation, all that can be thrown out of the window. It's either not going to work or it's not going to work at performance. So what we do is we use our tools to do both inspection, this is finding defects, and to do metrology, is to measure whether what's being manufactured is being manufactured correctly. Mathematically speaking, this is an outlier analysis. It's a very simple idea. Draw a distribution of different pixels, look at the 5 sigma, 6 sigma, 3 sigma, 2 sigma, depending on where in the process you are, and that's the outlier. It's outlier analysis. Mathematically, that is a measurement of the mean. Because you have like 100 devices, each of those have a little bit of variation in this. What you're trying to do is trying to control the variation to be within a particular variance. As long as you're within the variance, your chips will work. So it's not perfect. Like 3 nanometers does not mean you get perfectly 3 nanometers. You get anywhere between 3.02 to 3.03 to 2.99. Still works. So that's the work there. So this just shows you a schematic of our tool, right? So what our tool has is everything that is needed to do this operation. Starting from the optics or the illumination sources that produce the optics. We actually have a plasma that burns at about 50,000 Kelvin. That's hotter than the sun. We shine a laser on it and it emits broadband. We use that to shine the light on top of the wafer. Then the data that comes out gets collected by the sensors. These sensors are custom built CMOS sensors and that also use FPGAs to collect the data. This data is coming out at about 100 gigabytes per second. So to give you a notional idea, that translates to about 4 petabytes every 8 hours. That's how much data all Facebook users in the world generate in a day. One tool in one shift, that's 8 hours, generates that much data for us. And from that, we have to sift out and do all that outlier analysis and the measurements. We also have these mechanics staged, right? So what this is you put this wafer on a particular robotic arm and it's going to place it under the microscope to take the picture. So we're trying to find defects that's like 2-3 nanometers. So this thing cannot vibrate. It's got to be dead steady. How do you do that in a shop floor that is like vibrating? Hard problem. We also have all the compute that runs the image processing algorithms within this tool. So it's a distributed cluster, heterogeneous cluster, but it's an on-prem distributed cluster. So all the software runs inside the tool, the optics are inside the tool, and all the compute is inside the tool. So it's a cyber-physical system. It's pretty fascinating that the thing actually works. Right? It really enables us to make sure that every chip that's manufactured in the world goes through at least one KLA tool. There are certain steps in the manufacturing process that only KLA makes tools for. So literally every chip, whether it's your phone, whether you're seeing Instagram on, whether it's your watches, whether it's your laptop, every chip has been seen by a KLA tool. They've influenced your life in more ways than you can know. So that's the background. So if you have to take anything away from it, I want you to take away that semiconductor manufacturing is complex. Right? So that's the gist of what I just showed you. So now let's look at AI. Everybody used to talk about AI. We also do AI, but we do real AI. So let's look about how we leverage AI into semiconductor manufacturing. So this is a snapshot of all the algorithms that run inside our tool. This looks like a textbook page, but I'm not joking. Right, so we've been doing computer vision and image processing for about 49 years. Next year is 50 years for KLA. We are a Fortune 500 company. And literally every trick in the book, starting from random forest, Boost junction trace classification, conditional GANs, autoencoders, and new areas like pixel CNN, all of these algorithms run inside our tool. It's not all just one tool. We have about 100 tools in our portfolio that solve different problems in different challenges in different time. And a combination of algorithms runs all across. So what I thought I'd do for this talk to keep it fun was to take one example and to just show you what we do. So let's take the example of where do we use conditional GANs, right? It's a very interesting case. So we're trying to do inspect patch for defects. So you're given a patch. Somebody gives you a patch and say, okay, go find a defect. Is there a defect in this? So I look at this patch and I wonder, okay, how do I find a defect? This is a patch under test. If you have a reference, which is a golden defect-free image, I do A minus B, it's easy. Where do I go for reference? We know the design. We designed the chip, or somebody designed the chip. So let's go and look at the design. The design looks like this. So then I get curious. Hey, all these rectangles that are there, nothing is there over here. This is a real image. There are no straight lines, there are no parallel lines. It all looks like squiggly, and this is a real chip. So then what you do is you take this real circuit and you know a chip that's functioning correctly. This is an image of a scanning electron microscope that has a resolution of about 2 nanometers. We take the same microscope and we inspect a fault-free manufactured chip. And it looks like this. Are there any right angles in that? Are there any straight lines? No. So it basically means that the reason why this happens is because the wavelength of light that's used for manufacturing is much higher than the critical dimension you're trying to manufacture. So there is already an inherent stochasticity in the manufactured output. So the question is, I now have a defect-free image that looks very different from design. I can't use design to actually collect this. So what do? I can't afford to collect scanning electron microscope images for every single circuit because it's too slow. What do? So turn to AI. So take a bunch of circuits, take the corresponding bunch of scanning electron microscope manufactured systems. Of course, this is done at training time, so you can afford to spend the time to do it. Take a GAN, take a generative network, which is now capable of, given a circuit, this is the ground truth for that circuit, we were able to train a GAN that can actually generate the image. It's a very non-trivial problem because if you look at, for example, these tuning forks that are there over here, these two tuning forks, in the same ground truth, these two are not symmetric in this one, but it's symmetric over here. Right? It's very difficult for us to reason why that happens because this is, of course, an artifact of the light that's used to manufacture, the materials that are used, etc. But with data, we're able to overcome the fact that we are also able to generate a good reference for it. So that's great, right? So we got a good reference. So you got a patch to you got the corresponding patch from the design of what you're trying to test. We take that patch, we give it to the GAN. Wonderful. The GAN now gives me a reference. I say, yay, let's go and do. Now I have a reference, I have a test. A minus B. Right? Now I look at A minus B. And this is an example of actually a real, what we call a blinking image, where we have two images superimposed on each other. One is the reference generated from the GAN, and one is the defect under test. I've just zoomed the areas that are the defect. If you really squint your eyes, and hopefully at a distance you can see this easier, it's a little bit of a shot here, right? It's a little shot here. That's the one that I'm trying to detect. You do A minus B and you get all this noise. Right? All this noise, there's so much noise over there. And the red boxes are just drawn for our eyes to guide ourselves. That's the real defect. The rest of it is just noise. We call this nuisance because it makes our life very difficult. It's a nuisance. It's really troublesome. Right? Why does this happen? This happens because inherently the fault-free design is also stochastic. And there's a certain level of stochasticity that can be handled, which is not accounted for in the traditional algorithm. It's very difficult to account for because it cannot be mathematically modeled. So, turn to AI again. So with data-driven solutions, what we're able to do is we actually are able to identify the specific locations in the design where the defects are and to be able to remove the noise very well. Okay. One of the unique things that we do in this kind of AI is that because, remember, the stochasticity comes because of physics that is there in the manufacturing tool and the physics that is there in our light source that's capturing the image. And we know the physics because it's our tool. So in our AI, we use this physics as a prior. And therefore, what we do, what we call as physics-informed AI, or physics-based AI, where we use physics to guide the AI in the right direction, such that, for example, a simple analogy to think of is, if you're trying to do detection of trees from natural images, sky is blue. Tell the AI the sky is blue. Don't give it 50,000 images and say, learn the color of the sky. You just tell the AI the sky is blue. Similarly, we give priors to our algorithms based on what the physics of the tool is, and it's able to do a wonderful job of actually detecting this. So that's an example of devising an algorithm, saying, okay, I got an algorithm now that's able to do great defect detection. Now let's make these things run. Now this is a unique challenge that we have in KLA because the algorithms are going to run within the same tool and the hardware is inside the tool. So I'm not going to ship this out to a cloud and let it run in a Google Cloud or Azure Cloud or any other public or private cloud provider. It's inside the physical tool. Therefore, if my hardware that is inside the tool is not optimally used, I need to buy more hardware. Right? The data rate that the sensors shipping out is 100 gigabytes per second, and I need to consume 100 gigabytes per second. If I have only 40% or 50% occupancy of my GPU, I got to buy more GPU. So it's always in our interest to do very high optimization and what I call co-design between the hardware and the software, such that we pick hardware that is understanding the algorithm that is running on, and we pick algorithms that can leverage, for example, reduced pressure. Somebody spoke about reduced pressure earlier, right? Uday spoke about reduced pressure. We pick algorithms where we know that it's going to run in, say, 8 bits, or 4 bits, or 2 bits, or 1 bit. How do you deal with this at the algorithm level to avoid any impact to sensitivity, such that those two little squares I showed earlier, those two still show up? So that's a co-optimization that we actually do. So to look at that co-optimization, let's briefly talk about the compute stack. I spoke about these three: the optics, the sensors, and the data processing. But just to detail this out a little bit more, this is what we call the image computer, or the IMC. We start with raw inputs. This is the data collected from sensors. This is a real example of an optical image. I've shown you all so far beautifully resolved 2 nanometer scanning electron microscope images where you can see the defect. This is the same AB blinking with an optical image. The wavelength of the light here is 192 nanometers, so resolution is 100 nanometers. I'm trying to look for defects under 10 nanometers, and it looks like that. With the naked eye, it's impossible to say if A minus B is actually a defect or no defect. We bring this resolution using algorithms, right? And then finally, Mark quoted saying that the truth with AI is actually to get you information, not with data. I don't want to just throw out data. What we try to do is we collect this and classify the kind of defects we find into into some kind of a Pareto that gives information to the process engineer that there are these types of faults in wafer 1, there are those types of faults in wafer 2, such that they can go and correct the tool that's actually doing the manufacturing. In all of these, we use a combination of real-time processing that uses FPGAs, bulk processing with CPUs and GPUs, and structured processing that also uses CPUs and GPUs. But the question really we go after is to ask, what is the price that we're willing to pay for these models? So just some musings from different sources talking about what is the price that we're really willing to pay, right? Of course, the needs of AI is outpacing Moore's law. This is from Jim Keller, a slide that I'm sure many of you have seen and even used in some of your talks. There's so much advancement in AI that continuously throwing more and more compute seems necessary, but we can't afford to do it because we're within a single system that we have to buy and sell. The other interesting thing is, this is an angle that people don't think about. The software perspective is very interesting. So the table here shows the energy efficiency of coding algorithms in different programming languages. The topmost is C and Rust, which means that if you code an algorithm in C and Rust, you get very good energy efficiency. Python is fairly low. So all those of you who are writing Python code and giving me algorithms makes our life very difficult, right? For systems engineers, it's very difficult to program in Python, and this is something that we have to consider. At the same time, Python is a lot more easy for people to use and do experiments, but from a deployment angle, it becomes very challenging. And finally, just like the data centers of the world are really spending insatiable amounts of data for compute, we have the same problem inside our tools as well. Because we have to deploy these AI algorithms, but we can't afford to do all these, lot of GPUs and a lot of compute. We can't afford that. So we got to keep that control. So I have about 10 minutes to go, so I'm going to start accelerating a little bit, pun intended. So the importance of hardware software design in this work overall is to actually look at, we focus on getting well-designed software stack that really make the software capable of achieving the hardware's performance. So this was some work that we published in HIPC last year, where we looked at different accelerators. We looked at NVIDIA accelerator, AMD's accelerator, MI210, and an Intel GPU. And we said, like Uday mentioned, hyper-optimization is something that we do for our deployments. But if you really hyper-optimize, the question that we were after is, how close to the theoretical peak for that particular algorithm are you actually able to achieve? So we want to get as close as possible to the theoretical peak, because the farther you are from the theoretical peak, you're wasting dollars. It's interesting enough to find out that we were much closer to the theoretical peak with CUDA when compared to the other workloads. I'm sure those of you with AMD designing GPUs today are thinking, what the hell, this doesn't look right. So this was a stake in the ground with the MI210. I'm sure the MI300, the 400 looks better. But these are the kind of considerations that we have, right? It's about optimizing, but making sure that you actually can get to theoretical peak of what the system provides you. In addition, it's not just about code design, but it's also about portable code design. And this touches along the lines of what Uday spoke about in the morning, where performance portability is important because we want to make sure that we have the freedom to pick which GPU I want to put inside my tools. I don't want to have to use one GPU, and more importantly, I don't want to have to rewrite code every time I move from one to another. But I'm greedy. I want to get the best performance possible. I don't want to give up performance for this portability. So one of there are a couple of interesting avenues here that are emerging that we also have been looking at. Uday spoke about both of these in the morning as well. Where we look at OpenAI Triton as a programming model. It's a very interesting graph that shows you this data from IBM. But it actually showed you when you write full-fledged applications, when you write low-level kernels in CUDA and write it in Triton, how close in performance do you get? So until MLIR compilers mature and they're able to do the kind of optimizations that they're able to do by hand, which I'm sure Uday and team will be able to do a wonderful job of. We think that that compiler is not yet ready. It still needs a little bit of exploration and advancement. But Triton, which is like an intermediate programming language, which is a block-based programming language, seems to be a good middle ground for us to consider. We're actually able to see that this was, I think, a year old almost now, but recently there was a Triton conference where they were actually able to show on the Hopper and on the Blackwell generation GB200s, they're very close to cutlass performance. Which means that with Triton, which is arguably much easier to develop with, you get much closer to the peak performance that the machine can achieve when compared to writing low-level code. So, to wrap things up here, semiconductors, of course, critical part of the global economy. Digitalization, everything is becoming smart. Your fridge, your washing machine, your bags, everything is smart today. Semiconductors enable all that. Our tools have been used to make sure that Moore's law continues to advance. For those of you who hear that Moore's law is dead, it's not. I can tell you that. There's a roadmap from all the vendors saying that they're going to continue to progress the shrinking of the dimensions. It's becoming harder. I'm not going to say no. It's hard problems, but I think that's where the fun is. Fun challenges for us to look at, and we've been using AI and HPC. So it's an interesting thing that I'll close with. We have what I call the circle of AI and HPC. We actually use AI in our inspection systems and metrology to do chip manufacturing. That gives you the chips that then end up building the high performance computing servers that then run the AI that we run on it. Right? So we use AI to build AI, and we use HPC to build HPC. So it's an interesting circle of AI and HPC that we have. So with that, I think this is customary for me to have a pitch deck so that I earn my salary. So please feel free to connect with us. So we are based out of Chennai. I had the research lab located in IIT Madras Research Park. That's a picture over there. Right, we have close to 1,000 employees who work across different disciplines. My research lab is about 15 of us who are looking really at next to next generation advancements in algorithms, in high performance computing and systems. It's very difficult to find the right people. I'm actively looking for R&D collaboration. I collaborate pretty heavily across India with many academics. I'm looking for that. We also have openings for both internships and for full-time opportunities. That's my email ID. It's pretty easy to find. Okay, that's all I've got. I think I have a reasonable amount of time for questions. I'm happy to take any questions that you may have.
Close to 5 minutes for questions, so please feel free to ask questions.
If I don't get questions, I'm going to make you do exercise again. So.
Hi, wonderful talk. So the question I had was the insights that you are able to extract from inspecting the defects in the chips. Like, can you sort of like use them in the improving the manufacturing itself?
Oh, wonderful question. So the question was, can we, are the insights that we gain from inspection used for manufacturing? In fact, it is. That is the primary purpose of our tools, right? What our tools do is the process engineers who basically are running, say, the factories of TSMC or Global Foundries or whatever, use our tools to look at some intermediate stage of manufacturing to say, okay, is this all okay or not? And if it's not, what they actually do is to go back to a manufacturing tool that's either doing the etching or the CMP or the deposition and go fix something. They map the information that we provide to a step in the manufacturing that they go and fix. And all the manufacturing tools are actually spec'd on KLA tools. They say that this ASML stepper has this spec with a KLA 2960, for example. So that's a direct relation. So yes, that's actually what it's used for.
Thank you.
So how did they do the mapping back? Is that just?
I wish I knew. It's that's very proprietary for the. It's dependent on the process. It's proprietary to the factory that's doing it, so we don't get visibility into that. Because once we know what happens, one, I can improve my output, and two, if they teach us, I can go use it for some other fab which they don't want to do. But it's difficult. We try to use some of that fab, it's very difficult. Yes.
Thanks for the enlightening talk. My doubt was regarding that 100 Gbps, what you mentioned, right? It's staggering data. I was not sure, like, what's the need to actually process that inline, meaning even if a defect is, we can take it, do it in a lazy manner, probably get some breathing time and then fix it. It's
Very good question. So the question is, why do we have to process the data coming out inline? And why is it not done offline, right? Good question. So I'll tell you in two phases, right? So the first phase of where our tools get used is when you're ramping yield. When you're ramping yield, you're, let's say, at 25% yield and you want to get to 85% as fast as possible so that you can tell NVIDIA or Apple or AMD to come use the fab, right? In that process, what happens is our tool, you run a step of a particular layer, you stop everything, you take a KLA tool, you run inspection, you look at defects, you go fix the tool, you run it again. So at the ramp phase, our tool is stopped, the fab is stopped for output from our tool on the one side. On the second hand, so that right there is inline. Like that is in ramp phase, our tool is absolutely critical. But once you reach HVM, that's high volume manufacturing, where your yield is like 80-85%, right, plus, you don't expect to see that many faults. However, what happens is the stepper and the scanner that is actually doing the manufacturing, these are like, again, I showed you the example, it's like a CMP, it's like a chemical mechanical polish, right? So it's actually moving stuff. Since these are mechanical devices, they drift over time and they need to be corrected. So therefore what happens is when you're in HPM, this is called a process drift. So when the process drifts, you want to find out the process drift well before it starts affecting the yield. Because if let's say that your CMP that's actually going on here, right, introduces, I'll give you a very good example, again, think just mechanical intuition, the center of the wafer gets more pressure than the corner of the wafer. Because if you go like this, more likely that you're hitting the center of the wafer more often, so the center tends to shrink a lot more. But with time, this heavy disk keeps coming down. So you start initially maybe shrinking like half a micron, then like 0.75 micron. Maybe at 1 micron, you've taken too much away that the layer will no longer work. But you want to find out before that 1 micron happens. So at HPM, what happens is a sampled number of wafers are actually sent to our tool. Manufacturing continues, but the moment there's a problem, we stop the process. So the faster we can give responses, the quicker the answer is, and the quicker the response of the yield engineer is. Therefore, it's all in one.
Thanks.
Sure. Yes.
Thanks for the nice talk. Learned many things. So I was wondering, the example of defects that you showed was shorting. Are there other defects? Like, would you give us examples of defects that get caught by your image analysis?
Yeah. So the question was, I showed you an example of a short. Are there other examples of defect? Yeah, there's all kinds of things, right? Like, let me give you a very fantastic example. When you do NAND, right? NAND actually has a 100 nanometer deep well, okay? And then there's a gate at the bottom. And you have these two parallel walls of two wells, the walls of the well that are both 100 nanometers deep. 100 nanometers for us is like kilometers long, right? I'm thinking of 1, 2 nanometers long. It's a 100 nanometer long well, right? If these two are not parallel, they're like yay off. That's a problem. That's an example. That's a defect for me. Or there's a gate at the bottom, the corner on the one side is not sufficiently touching, you end up with an open. Those are examples, right? It's not always electrically reasonable as to why these are problems, but any deviation from the design is a defect. So if you have parallel lines, cut, short, not strain length, all of that are defects.
So despite all these optimizations, what's the error rate in chip manufacturing today?
What is, despite all these optimizations, what is the error rate? I don't know the exact numbers of yield, for example, but anecdotally, what we hear in the market is that 80% plus is considered high volume manufacturing, which means that even when you are running at full capacity and your fab is successful, 20 out of 100 chips will fail because of manufacturing problems. And that's really good, right? But when you're manufacturing early in stage, right? Like for example, you'll see that sometimes there are chips that are released at very early stages of a particular node, like Apple, famous example, right? You'll hear Apple is the first one to bring out a 3 nanometer chip. I don't think their yields will be at that numbers. I'm just guessing. I don't think it will be that numbers. But for them, bringing it to market is important. So it's all a game of economics. Can you get to 100% yield? Yes. How long will it take you? And are you willing to give up using the fab for that much time? Increasingly, the answer is becoming, I don't want to waste that time. Earlier, you could wait till like 90-95%, but it's very difficult.
Okay, if there are no further questions, let's thank Pradeep again for the wonderful talk.
Thank you.
Okay, so the next talk for the session will be given by Professor Saurav Bansal. So he's a professor at IIT Delhi. He has a PhD from Stanford, and he has over 15 years of experience in compiler super optimization, and he spent his career teaching machines how to run codes faster, right? And now he's taking a slight break from IIT Delhi, and he is teaching how to make these machines run trades much faster at Graviton Research Capital, which I think he'll tell us a little bit more about today. And the most exciting thing for me that I learned today was that compilers folks have a lot of guts, because Saurav has also promised another live demo today. So I'm looking forward to it. And these guys are setting the bar very high for compilers research folks. So yeah, take it away, Saurav.
Well, thank you very much for this kind introduction. It's been a great workshop, wonderful talks. Thank you for organizing and for attending and for giving the talks. My talk is on imagining a next generation super optimizer, and I hope I've set the expectations right, as the title only promises an imagination. My primary affiliation is IIT Delhi. I'm currently on a leave from IIT Delhi, spending time at Graviton Research Capital. and their research lab, I guess. And there's a third affiliation that I didn't list on the slide because it's too crowded to list too many affiliations, but that's a startup that we're doing based on our research that I'm presenting today. But overall, all these things are just basically doing the same thing that I'm going to be talking about in the talk today. So you'll get some sense of what I do. So you may have noticed that compilers have been growing in complexity over the past 3 decades. This chart demonstrates the number of lines of code in the GCC compiler over time. Starting from 1992, the number of lines of code has increased linearly, basically as fast as humans could develop it. Today, GCC stands at over 22 million lines of code, which is an astounding amount of complexity, much of which is due to its code generation and optimization logic. At this point, I'm sometimes asked about this dip in the lines of code at around 2016-17, and this is because a garbage collector named Boeing was deprecated at the time. It's nothing fundamental. As you can see, the complexity soon caught up. LLVM is another important compiler infrastructure that has risen to popularity both because of its cleaner abstractions and permissive license vis-a-vis GCC. Indeed, LLVM developers have distinct advantages over GCC developers by virtue of starting late, and thus leveraging modern tools and techniques and also avoiding known mistakes. Yet, the development model hasn't changed, and we see a similar growth in complexity for LLVM too. Here I show the lines of code in LLVM's core components, mostly the include and lib directories in LLVM over time. Once again, we see a linear increase in complexity that is showing no signs of slowing down. The total lines of code of LLVM's core components stands at around 4 million lines of code today. It is thus no surprise that we witness some kind of fatigue in compiler development. Students are afraid to enter this space, as even the best contributions may seem incremental in this setting. And it is not just about the new entrants. This example of a conversation shows how an existing compiler developer can feel disinterested in implementing yet another improvement that optimizes only a particular coding pattern. A compiler requires millions of such incremental improvements to become and remain a top quality production compiler. However, each improvement involves laborious design and implementation, which is the root cause of the growth in compiler complexity over the past 3 decades, and keeps the pace of compiler development slower than desired. I want to clarify that I'm not at all saying that compiler development has saturated. In fact, my next couple of slides motivate through examples that there remains a lots of headroom for a compiler to improve. We just need a better development model. A simple implementation of strlen is shown on the left in C, and an optimized implementation as available in the GNU C library is shown on the right. The glibc implementation first aligns the input pointer to a 4-byte boundary in its first loop, and then in its second loop reads 4 bytes in one instruction and checks whether any of them are null by using this clever use of masks, arithmetic, and logical operations. If the expected size of the input strings is long, then this implementation on the right can offer a 3 to 4x speed up over the simple implementation on the left. However, today's compilers are unable to perform such optimizations automatically. Here's another example. On the left is a functional specification of the strlen function. The functional language is our own. It is similar to OCaml, but perhaps not identical. It does not matter. The functional specification just says that a string is formed by a nil-terminated list of characters, but does not specify how the list is implemented, whether it's an array or a list or something in the middle. On the right is an implementation of strlen in C that uses a chunked list to represent a string. It uses the same trick of reading 4 bytes in a single read, but it also stores a string non-contiguously to save space through sharing. It can be shown that these two implementations are mathematically equivalent. However, this seems well out of reach of today's compilers. There are many other examples of hand-coded optimizations that are in everyday use, but are either out of scope or poorly supported by a compiler today, even after decades of development. Complex rewrites involving SIMD vector instructions, etc. I'm not going to read all of them, and not all of them are present on the slide in any case. One potential solution to this problem is to try and get machines to help us in this compiler development task. An overwhelmingly large fraction of the compiler complexity is its optimization logic. So if we could get the machines to automatically identify optimization opportunities, that would relieve the human programmers of this complex task and could potentially make the compiler development process faster. Here we have 2 sets of algorithms. One set are the inductive synthesis algorithms that use certain heuristics and search strategies to automatically propose candidate solutions. you can imagine that these inductive synthesis algorithms are approximate. For example, they may be based on machine learning techniques. And so the candidate solution may be incorrect. However, a compiler cannot tolerate an incorrect optimization, and so we use a validator, also called an equivalence checker, that checks every candidate solution. This is the second set of required algorithms in this design. The equivalence checker checks the candidate solution for equivalence against the program specification. If it is able to prove that the two programs are equivalent, we obtain an optimized solution. On the other hand, if the equivalence checker is unable to prove that the program specification and the optimized assembly implementation are equivalent, it should typically generate a counterexample that demonstrates this inequivalence. A counterexample here is just a program input that would cause the specification and the implementation to behave differently. This counterexample can then be used by the inductive synthesis algorithms to appropriately fine-tune their search so better candidates are generated in the future. This vision has been painted by several researchers in a common theme of work called program superoptimization. The name superoptimization was coined by Henry Massillin in 1987, where he was interested in finding the optimal implementation for a given problem using machine power. Now, the term superoptimization is used for a technique that uses machine power to discover optimizations, even though it may not necessarily be searching for the optimal solution. For inductive synthesis, several algorithms have been proposed, starting from brute force enumeration, stochastic search, learning from examples, mutation-based learning, constraint solving, and many more. Recently, the breakthroughs in neural networks and large language models have made them a very promising approach to try and attack this problem, and I'll talk more about one such recent effort in detail. Meta's LLM compiler is an LLM that has been trained and fine-tuned for three distinct tasks. The first task is emulating a compiler that involves specifying as input the unoptimized LLVM IR, the optimization flags, and obtaining as output of the LLM the output IR or assembly. The second task is for tuning compiler flags for optimizing code size. They give as input the program as unoptimized LLVM IR and request the model to predict the required optimization flags for code size reduction for that particular program. And it also expects the model to emit the output LLVM IR, which has been optimized for code size. Finally, the model is trained for disassembling assembly to LLVM IR. And I'll share more details on all three of them in my next few slides. Here is the prompt used for LLVM to LLVM compiler emulation. If you know how LLMs work, you basically design a prompt and you have some blanks in those prompts, and you use lots of correct examples with those prompts, and somehow magically the LLM learns what the patterns are and is able to answer prompts that it hasn't seen before, right? So here the prompt is for LLVM to LLVM compiler emulation, where the prompt says, give me the LLVM IR for the following code when optimized using this set of passes or this sequence of passes. And then you give the LLVM IR. And then the prompt also says, this is the input code has this much instructions, these many instructions, and this is the size, binary size in bytes when compiled to x86. And the answer you expect is the LLVM IR will have, the optimized LLVM IR will have this instruction count and this size, and here is the answer. And you just train the LLM using actual examples, which you can just obtain by using a real compiler. Here is the prompt used for LLVM to x86 compiler emulation. Once again, the prompt is give the assembly for the following code when optimized using this sequence of passes. The input code has these many instructions, etc. And the answer that is expected is the assembly will have this instruction count and this much size, and here's the output assembly. Okay, good. So simple enough. What are the results? The results show that they start with this LLM model called Code Llama, and they first pre-train that thing to kind of show it lots of LLVM machine examples and lots of x86 code examples, so that at least the model knows what the syntax of these two things are. And then they fine-tune it by using the prompts that I showed earlier, to kind of have the associations and so on. On the right hand side, you see what are the results for doing this compiler emulation. And well, the bottom row is when you do all this training and all that, then the stuff that gets emitted as an answer compiles 95.6% of the time and is an exact match to what a real compiler would have produced 20% of the time. So it seems like the model has learned the syntax of the x86 assembly or the LLVM IR, and it's doing, you know, 1/5. It's become 1/5 of a compiler, let's say. Also notice that without fine tuning, it has learned the syntax. For example, it's 36% in the second row, but it has no clue about what the associations are. And the original code llama is much poorer in its results, and so on. Okay. Here's another experiment that was attempted with the Meta's LLM compiler, which is an auto tuner. So firstly, so basically it is well known that if you just use the size flag, if you try to optimize using the size flag, then you get certain optimization, but that's not the best possible optimization that the compiler can produce. And just figuring out what's the set of flags that you should give to the compiler to get the best possible code is itself a pretty hard problem. And so in this problem, they're just trying to figure out what is the right set of compiler options that I should give so that I get the best possible size. And so what they do first is, without using LLMs, they try 5,000 different sequences of passes for every program and figure out which of those sequences gives the best answer. And just using this, they are able to get a 7.1% reduction in binary size over the default OZ option in the compiler. Well, this is a very expensive process because, you know, you are trying 5,000 random sequences per program, and you can imagine that this is very compute intensive. It takes 21,000 CPU days for around 1 million unique best pass lists. The idea here is that can we get the LLM to learn what's the right, given a program, what's the right sequence of passes for that program, so that you don't have to pay for this extra 21,000 CPU days. You just ask the LLM what's the right sequence, and then you use that, and you get hopefully some of the 7.1% reduction for free. So once again, here are the results. Evaluated on MI Bench, an embedded benchmark suite, LLM compiler with 13 billion parameters generates smaller object files than -OZ in 61% cases, and generates larger object files than -OZ in 12% cases. Notice that correctness is not a problem here. The LLM is just being used to figure out the sequence of passes that needs to be used to generate the code. The fact that it can sometimes generate larger programs is not that big a problem, because you can just run it twice and just pick the smaller one, once with -OZ and once without, with the one that the sequence of options that LLM gave you. For some benchmarks, the improvements are as high as 13%. The improvements with the 7 billion parameter model are often higher than the improvements obtained with the more the parameters, the higher the improvement in general. The bigger the LLM, the higher the improvement. Okay. Finally, you know, I want to, the third experiment that they did was they learned the inverse relationship of this command, which is the compilation. So what's the inverse of a compilation, and can we get the LLM to learn the inverse of a compilation, which will become a disassembly. So if you use this command clang-xir source file -o target name, then you use, and then the prompt that you use is disassemble the code to the LLVM IR. So you give the x86 assembly as the input, and you expect the output as the disassembled LLVM IR. In this case, the LLVM was optimized, etc. I'll skip the details. These are the results for disassembly. For 936 out of 2015 input assembly programs, the output LLVM IR was well formed. So again, it has learned the syntax properly. And it was possible to convert it back to assembly. So whatever LLVM was given out by the LLM, it was possible to use the LLVM compiler to convert it back to assembly. Further, 14% of these programs produce exactly the same assembly as the input upon round tripping. So you take the assembly, you run it through the LLM, you get the LLVM IR, you again compile it, you get the assembly, and do you get the same exact match? Well, that happened for 14% of the cases. This is called round tripping. These numbers are near zero if you don't, for the original code llama LLM. So clearly the fine tuning, etc. is helping. Okay, so summary. Overall, around 96% compiles and 20% are exact match for compiler emulation. And for disassembly, there's 14% round trip match. And both of these seem like very promising results, especially given how many decades we have spent in developing compilers and how easy it was to train just a 13 billion parameter LLM model. But it's obviously not satisfactory. There are significant macro improvements, opportunities for improvement in this space. First, the requirement of exact and round trip matches are too strict. Instead, we need a way to check the semantic equivalence match. Second, the LLM is used in a one-shot input-output setting, and there's no feedback from the LLM to the LLM from the equivalence check. These seem like obvious areas of improvement. I think it's, so because all these synthesis strategies are noisy, there's need to validate the proposed optimizations. This validator is also called the equivalence checker. The equivalence checker must be sound. That is, it must return true only if the problem and solution programs are equivalent. However, it is hard to have an equivalence checker that is both sound and complete at the same time. In other words, the equivalence checker may return false even if the programs were equivalent. That is, it may have false negatives. The more robust an equivalence checker, that is, the fewer times it has false negatives, the more optimizations the super optimizer can potentially learn. Thus, the power of a super optimizer is in a big way dependent on the capabilities of an equivalence checker. For example, if an equivalence checker incorrectly discards a valid solution, our system will never be able to identify and learn the corresponding optimization, no matter how good our inductive synthesis algorithm is. As a recap, the full picture of a super optimizer includes an equivalence checker that iteratively interacts with the inductive synthesis algorithm to eventually produce a solution. Recall that we said that the capabilities of the equivalence checker determine the power of the super optimizer based development approach. The equivalence checker needs to support checks for end-to-end equivalence between an unoptimized program specification and a fully optimized implementation without assuming any knowledge of the intermediate steps used in the transformation pipeline. That is, it should be black box. It needs to support loops, aliasing information, floating point, and all the general constructs of an imperative program language, such as function calls. The transformations it supports should include loop transformations like splitting, peeling, unrolling, unswitching, vectorization, etc. It should model memory precisely, including the presence of the ampersand operator in the source code. Importantly, the equivalence checker must have no false positives. In other words, it must return true only for truly equivalent programs. In other words, the equivalence checker must be sound. A false negative is a situation where an equivalence checker returns false when the programs were actually equivalent. It is perhaps not possible to build an equivalence checker that is both sound and has zero false negatives because the problem is undecidable in Turing's model of computation. The equivalence checker should aim to minimize such false positives. The problem of equivalence checking has a well-known and important application in translation validation, besides the super optimizer application that I just showed you previously. Because compilers are so complex and may have bugs, a translation validator checks the source code against the machine code for equivalence. Because this is a well-understood experimental setting, we have been developing and testing our equivalence checker in this context too. Translation validation remains an open problem, and the development of an equivalence checker that performs automatic translation validation would be a significant step forward in the development of provably correct compilers. Our research over the past many years has targeted this space, even though our broader motivations relate to super optimization based compilers. We have tested our equivalence checker against mature optimizing compilers on large programs. We have also tested it across aggressive vectorizing transformations, either implemented manually or through a compiler. My next thing is going to be a short demonstration of our equivalence checker. So here I have the strlen function that I showed you earlier, which is the simple possible implementation. And here is the optimized implementation as obtained, as seen in glibc. And you can start an equivalence check between the two programs. An equivalence check here basically means that for all possible input states of the machine, the two programs produce the same output, for example, the same return value, and have the same effect on the state of the machine. For example, they update the global variables and the heap in the same exact way. While I'm showing this equivalence check for two C programs, our equivalence checker can also do an equivalence check between a C program and an assembly program, in which case equivalence would mean that the two programs modify the global variables and the heap identically, but may have different effects on the local storage, example, the stack and the local variables. What does it mean to say that the two programs are equivalent? It's a formal proof of equivalence between the two programs. And a formal proof of equivalence basically looks like a lockstep correlation between the two programs, which is shown, and this lockstep correlation is encoded as a product control flow graph shown in the middle. So for example, this product graph is basically a graph that executes both the programs in lockstep. So one step of this program is equivalent to, let's say, 4 steps of that program, and so on and so on. So for example, this first edge in this product program says that if this write program goes from the beginning to the head of the first loop, then the program on the left also goes to the beginning of the loop that it has. This edge here says that one iteration of the write program is equivalent to one iteration of the left program. This edge here says that if the write program exits the first loop and moves on to the second loop, then this first program does nothing, it just stands still. This edge here indicates that if the first loop of the write program returns, then the left program also returns. For one iteration of the larger loop in this write program is equivalent to 4 iterations of the program on the left. And if the write program returns on any of the return statements in it, then the left program makes less than 4 iterations and exits. Now I'm only showing the path correlations, but this product control flow graph also includes the relations between the variables across the two programs. For example, the fact that PTR on the right is equivalent to P on the left when the product program is at S6 and D9. So it basically means that the source program is at line 6 and the destination program is at line 9. Now, while I've shown this for 2 C programs, because it's just easier to read C programs, the same thing can be done for a C program and an assembly program, right? So I'm showing a very small C program and an assembly program on the right. The assembly program has been generated using GCC with vectorization and so on. And you can see that the assembly program has vector opcodes and things like that. And you can, for example, the product control flow graph is saying that one iteration of the assembly loop is equivalent to 4 iterations of the source loop, and so on. While I'm showing this for small programs, our equivalence checker can tackle this for large programs. We've tested this on the spec benchmark suite and many bigger programs as well. Okay. Over the years, we have found several bugs in compilers and other software, such as the QEMU binary translator, a C library, and an SMT solver. All these bugs were found using our equivalence checker that I just demonstrated. In all these cases, when an expected equivalence proof failed, we tried to identify the reason for the failure. We would typically expect a shortcoming of our tool, but sometimes we found that the bug was in the program pair that was being tested. Except the GCC bug, all other bugs were previously unknown and were fixed immediately upon reporting by us. You can find more details on these bugs at this URL. Here is an example of a bug report, where we mention the library and the example input which triggers the bug. In this example, we are basically showing a bug in the strrchr function of the klibc library, the kernel's C library. And the bug here happens to be when the character that you're searching for is itself the null character. And here are examples of bug responses that we got when we reported these bugs to the developers of these libraries. Typically, they would either accept our patch or thank us for the report. Sorry. Here's an example of a bug and its fix, as seen in this GitHub commit. Here, this is again the strrchr function, and instead of a while, there's a corner case that they have missed, which is instead of a while you could have replaced it with a for loop, which never terminates, but then you add a break statement, and that would fix the bug that we reported. And here's a bug reaction. this bug was in this example of a bug reaction is from the NetBSD, from a bug that we found in NetBSD's swab function. And the author of this bug commit says, evidently the previous definition, presumably tightly optimized for the 1980s era compilers and CPUs, was too hard to understand because it was incorrectly tested for 2 decades and broken for years. So some of these bugs were kind of lurking around for more than 2 decades. And even though they are highly popular code, highly used code, and highly tested code. So among other things, this shows the value of formal verification and of formal verification tools. To conclude, I'm missing this slide, sorry. To conclude, I hope we all agree that there is significant scope for improvement in compilers. And given the recent advances, a super optimization based or AI based compilation is perhaps around the corner. These are the references for the material I have used in this talk. That's all. Yeah, thank you.
We have quite some time for questions, so if you have questions, please.
Thanks, Saurabh. Fascinating to see demos. Like I said, I don't know how you guys do it. The question I have is your equivalence checker you showed between 2 C programs that had very similar structural semantics of each other, right? So just thinking forward, like you mentioned, this also works for C to assembly, but does it also work for other imperative, or can it also work for other imperative programming languages? Where I'm going with this question is, we have this scenario where, like for example, when you're writing low-level programs, we do a lot of code movement and optimizations to be able to get the same functionality. For example, if you're writing CUDA, you do a lot of code hoisting and reorganization inside the code that a programmer is able to see is correct, right? Can the methodology that you're using also be used to do equivalence checks in those scenarios where the control flow is not really close? Here, your control flow is very similar, right? It's more, so in vectorized code, I can see this happening, but when you do even more like global code movement or loop independent code motion, the control flow could also change. Will this kind of equivalence structure, equivalence checker work in that scenario too?
Thanks for that question. I think it's a very relevant question. So what are the limitations of the equivalence checker, and what can it not do, and what can it do? So basically, you are very right in observing that our equivalence proof is basically a lockstep correlation between the 2 programs, which basically means that we need to have some we need to be able to find some correlation between steps in one program with steps of another program up to a finite unrolling, right? So for example, we go up to a finite unrolling of 64 or something like that. It turns out that almost a large fraction, maybe 99% of the compiler optimizations that we observe in general purpose programs fall under this category. And the technical term for this category is bisimilar optimizations or bisimilar transformations. Loop invariant code motion, vectorization, loop unrolling, healing, etc. They all fall under the bisimilar category, which can be decided as equivalent using this methodology. But there are many others, and so example being loop fusion, for example, or polyhedral transformations, where the order of the program computation completely transforms, and there's no finite number on which you can kind of relate the 2 programs in lockstep. And indeed, our equivalence checker cannot tackle those kind of things today.
Cool,
Yeah,
thanks.
but this is something that people are working on, and yeah, hopefully we'll see something.
Cool, thank you.
So I was thinking, inside graphs you mentioned the linearity of the code size of the compiler, right? So do you think there's a need for a better programming language support to write optimizing compiler?
Is there a need for better programming language support for writing optimizing compiler?
So that you can capture more of that complex optimization with lesser number of code.
So that you can capture?
Your compiler optimizations if you want to specify with lesser amount of.
Sure. I mean, so if you look at the economy of programming languages, right? Today we are living in a world where we have like plethora of programming languages. We have, the talk before me just showed a list of all the programming languages and what are the trade-offs between the 2. And the primary reason for that is some are easier to optimize than others. right? So writing an optimizing compiler for Python is much, much harder than writing an optimizing compiler for C and C++. And that's, so certainly like programming language design plays a big role in how easy it is to write an optimizing compiler. But I mean, my contention is that's not something that we should be accepting as the state of affairs, and hopefully we should be pushing the boundaries on that. And it's just, my contention is that it's just an artifact of the current development model of the compiler that we are having to live with this kind of situation.
Any further questions? Okay, if there are no further questions, let's thank Saurav again.
Thank you.
So by the way, I'm talking about Chelsea goes next. Michael and I didn't have sex. Thank you. He wants to do talks.
Okay, good afternoon, everyone. Welcome to the last session of this very exciting computer systems workshop. My name is Govindarajan. I am the session chair for this session. We have two exciting talks. The first one is going to be given by Jayesh Gaur. He is chief architect at IBM, designing server cores and server processors there. He has more than 2 decades of experience designing these processor cores, and he is in the IISc Hall of Fame. He's probably the second person in the room who is in the IISc Hall of Fame. There are many who are waiting to join that line. Maybe they will do that soon. He has multiple HPCA Micro Best Paper Awards. He got his degrees from IT Kanpur and University of Michigan. Over to you, Jayesh.
Am I audible? Perfect. Okay, so welcome back from the break, and I'm going to talk about CPUs. And because everything is about AI, let's try to see what is happening in the CPU domain when everybody's talking about AI, right? So, okay, so let's get started with this, right? So this is not the first time that computing has actually changed, right? I mean, earlier we used to talk about, let's see, this is laser, yeah. We always used to talk about frequencies, gigahertz for a very long time, right? And then suddenly we figured out, oh, we cannot build gigahertz machines beyond a point. So we started talking about multi-cores. You have lots of cores, right? And you basically try to do a computing across all the cores. And now we have moved to a different era where we're talking about acceleration, memory, GPUs, and everything, right? So what happens to general purpose CPU computing, right? Where does it go from here? So, and this is what we are trying to talk about in this talk. Okay, so why CPUs, right? What does the CPU bring to the table still, right? There are a few very important things which are very strong characteristics of CPUs. The first one is flexibility, right? I mean, the same CPU can be used to run any kind of workload, right? So, and it's heavily used today in what we can call as classical computing, databases, operating system, virtual machines, web servers, right? There's a lot of deployment across the world for these applications that happens in the CPU, and that continues to be a very important computing paradigm for all of us. Versatility, right? A lot of new security applications, for example, run the CPU, right? There's a lot of change that's happening in the CPUs to be able to allow that to happen. And when it comes to AI, we always think, when you think about AI, we always think about training, right? There is this huge amount of compute that you need for training, but a very important part of AI is inference. Once you have these trained models, can you use these trained models to go predict something, right, or give an output? And CPUs are a very cost-effective way of actually doing AI inference and machine learning, right? So, and that's an area where a lot of CPU companies, a lot of people working in the CPUs focus on nowadays, right? How can I make inference good on the CPUs? And it ends up being cost-effective because you anyways need a CPU. You need a CPU at least for orchestrating, right? And if that CPU is capable enough to do a lot of inferencing, that becomes a very cost-effective platform for customers. So this is an important use case that continues to drive how CPUs shape up. And then power efficient, right? We normally don't think of CPUs as power efficient computers, right? But if you look at things like edge AI, right? You have a drone which needs to run a small amount of machine learning, right? The same CPU that's there in the drone can be able to do that, right? So it ends up being much more efficient than actually putting in an accelerator to be able to do that, right? So these are important areas where the CPU continues to dominate, continues to improve upon, right? And they have their own set of challenges, right? So if you start, for example, with classic computing, this is something that we've always studied in textbooks, right? If you're looking at any server throughput, what does it depend on? Instructions per cycle, frequency, how many cores you have in the same server, and then of course nothing is perfect, right? So you will have a scaling of efficiency at the end, right? Depending on how well your workloads are scaling, right? And what about IPC, right? And this continues to be dominated by so many factors, right? And there's been so much of research that has gone on, but we continue to have the same problems, right? Every generation CPUs are trying to bring in 15, 20, 25% performance improvement every generation, and that feeds into all the computing tasks that we talk about, right? So they need that to be able to deliver more and more performance, right? So now let's talk about some of these topics that I put out here for IPC, right? Branch prediction, instruction fetching. classic problems, right? Branch prediction, a lot of people think it's just a solved problem, right? I mean, well, branch predictors we use all day is more than 99% accurate. I mean, that's great, right? Does that really help? Look at this paper, right? This is a slightly older paper that we did in IISc 2020, right? And what it shows is that if you take any regular CPU today and you start scaling all its resources, it goes like this, which is fine. You're getting some amount of performance. But if your branch predictors are all great and fantastic, look at the scaling that goes up there, right? As compared to what happens here, right? That small amount of 0.5%, 0.6% branch misprediction, that costs you a lot. Right? Because you have to flush, you have to start, you have to do a lot of things, right? And this is an important area. It's not easy to solve these problems, and that's the reason why you don't get 2x, 3x performance every generation of the CPUs, right? And then on top of it, a lot of other problems which fetchers have, right? Especially if you're working in the server domain, right? This is classic. You have new ways of programming, you have microservices, you have all kinds of large code footprint workloads that are running, and these create a lot of problems for all of us, right, on the server, right? So this area continues to be an important bottleneck that over generations as CPU architects we continue to try to solve. Execution with buffers. This seems like an easy problem. Now I can increase my CPUs to start doing more than 8 instructions, 10 instructions, 12 instructions per cycle. The problem is this is not so easy to build, because once you start increasing the execution width of the machine, things just don't go linearly, right? They go as square, right? You have to add additional ports, you have to add additional latencies to be able to do that, and these are all things which are problematic for a very low latency design like the CPU. So what's happening, right? So this is last year's paper, right? And we got a best paper for this. And what we actually showed out here was we took an off-the-shelf processors and we said, okay, see, the load execution ports are not increasing that much, right? They're slightly increasing even though the additional buffers are increasing. Why is it not increasing? Well, if I increase load execution ports at the core, I have to increase my cache bandwidth, I have to add additional ports to the cache, that will increase my latency, that's a problem, right? I have to make better TLBs to be able to do that. So what this paper went ahead and said, okay, let's try to solve this problem architecturally, and it identified that almost a third of the loads are repeating. They're actually reading the same address again and again, same data also again and again, right? So it went ahead and started saying, okay, can I eliminate these loads, right? Can I just execute them once, store this information somehow, right, and be able to do that? Now, this is not an easy problem, and that's why this paper was so well recognized, right? But if you solve this, there's a lot of performance that you can actually get from there, right? And without actually going and adding additional ports, you can architecturally increase the overall load bandwidth of the overall code. Right? So these are the smart problems, smart solutions that are needed to the problems of improving the IPC figures. Okay, what else do I have here? Cache prefetching, data speculation. Right? This continues to be, I mean, almost every conference we continue to have some really good papers that come out on new types of cache prefetching, new ways of doing value prediction, new ways of building cache hierarchy. And why is that? Because it is important, right? In fact, this is a couple of years old paper that we did, right, where we actually showed it's not just memory to the LLC which is important, which is quite a lot of performance for these select workloads, but if you can actually even hide your L1 latency, which is a small cache, but serves a majority of your loads, it has almost similar performance impact as solving the whole memory latency problem, right? And not just that, within the on-die cache hierarchy, because you're building more and more caches, the latency of that and hiding that also matters a lot to overall performance, right? And that's basically what it shows. Okay, so these are all the areas which continue to dominate. What are the bottlenecks for CPU, and continuing to improve them is actually a very important thing for a lot of companies, right? Including the work that we do at IBM. Okay, what are the other things, right? Server throughput is not just about IPC, it's also about frequency. Now, this is something that used to dominate earlier when we used to talk about very high frequencies. A lot of people think that frequencies are not increasing, which is actually not true. If you go and look at all the recent processors that are coming out from any company, there's actually been a small uptick in frequency every generation. And it's very, very hard to do that because you have lots of power density challenges, your process doesn't give you free latencies anymore, right? So what people have started focusing towards is what's called as workload optimized frequencies. And this is very important. A lot of people also call these turbo frequencies, which means that, okay, you've got a certain workload, a certain part of the workload, which is very, very limited by performance. try boosting the frequency only for that duration so that you don't burn through your power density problems for a very long time, because that creates reliability challenges and power delivery challenges. Right? So even though this is a somewhat saturating area in terms of performance, this continues to give performance, and there is a continued effort throughout to be able to do that. So this is important. Core counts. This has been almost like a war right now, right? With sockets packing more and more and more cores, and the problem is you keep packing more and more cores, it does not have a great efficiency when you have too many cores, because your fabrics are being shared, your memory bandwidths are being shared. You need to go towards chiplets, which basically means added latencies that you have to somehow be able to mitigate. So lots of challenges, right? But this is where it's all going, and it makes a lot of sense, because eventually the economics dictates that you basically have more cores per socket, which effectively lowers down your total cost of ownership, which is very important for any data service. And then finally, right, I had this thing at the end, right, the efficiency. This is just some kind of a parameter, right, which really depends on the workload, depends on the server we're talking about and everything else. And it basically includes everything from the fact that Amdahl's law would mean that you won't scale nicely with core counts. There'll be inefficiencies in the SoC. Your hypervisors will add a bunch of additional traffic that you have to take into account. Your memory, your storage, all of that will become a limiter, right? So you don't scale exactly. You will scale somewhat lesser than one than the actual formula here. But this is what has to be improved upon, right? So now, having said this, okay, this is all classic computing. This is great. We're solving problems. There's a nice set of research happening, right? Papers are being published. Industry is moving forward. Where does AI fit into the picture, right? AI does fit into the picture, and let's talk about where AI can actually help further the CPU, right? Lots of different ways, and we just heard of a couple of ways just before us, right? So we talked, right, prefetching is very, very important for performance. Branch prediction is very, very important for performance, right? And these two are great areas where a lot of machine learning has been recently used, and they've all shown that there is actually a lot of potential to go solve problems in these areas. Now, of course, many of these solutions may not be very efficient to be built on hardware, but basically what they have happened is they've shown a path, right, of using machine learning to be able to solve some of these very hard computer architecture problems. Okay. Then we just talked about, I think Pradeep talked about manufacturing and AI, just a couple of talks before. We just talked about compilers and AI. Again, these are all great areas where you can actually use some form of machine learning to improve some of these areas. But it's also being used heavily in design. For example, CPU design, RTL writing, bug hunting, EDA, finding out certain trade-offs between architecture, right? A lot of these things is where AI actually helps, and within IBM, we've actually been using this quite a lot, and we've seen really big productivity boosts by using some form of an AI in many of these things, including generative AI. And then one of my favorite areas where I think machine learning is very important is performance tuning. We just talked about workload optimized frequency. How do you figure out which part of the workload you want to turbo your frequency to, right? Or how do you actually figure out what can I do? Right? There's just all talk about small cores, big cores, and somehow workloads migrate between these two. All of these things are actually done through sophisticated machine learning that's built within the firmware or built within the software or built within the operating system. And this is where it's very, very important to utilize these techniques to be able to improve your CPU, adapt the CPU towards the workload. This is a slightly older paper, but I picked it up because this was my paper, so I can cut and paste whatever I want from there. But basically here we had shown that if you could actually adapt your, if you had a two cluster kind of a core, you could actually adapt the core for certain tasks which probably don't need that amount of compute, and make it like operate as a half cluster, which gives you like a lot of power benefits, and overall you get like excellent performance. And then basically you can actually go back and forth between a wide machine and a narrow machine so fast that you actually do not have any kind of an SLA violation with that, right? And overall you win in terms of performance per watt. So this is just an example, but basically machine learning is very, very, very important to be able to realize any sort of post-silicon tuning or adapting the CPU according to the workload and the server requirements. Okay, so So that was one part of it, right? Where we said, okay, AI helping the CPU needing improvements to overall increase its performance. It's the other way as well, right? And we talked about it in the beginning. We said inference is something that can be done on the CPU, and it's a very important use case for the CPU. And why is that, right? Because it depends on what you're doing, right? If you're doing training, you probably want to do it on a GPU because the CPU does not have enough compute, enough bandwidth to be able to do that. But if you're doing inference, right, or even large inference, depending on the system that you're actually running it on, this could be very useful and very cost effective to be able to do that, right? So for example, at IBM with Power 10, we introduced what we call as in-code MMAs. These are actual MMA instructions, matrix math instructions into the processor cores that allow you to be able to do faster inference because, of course, they'll be more efficient in terms of doing matrix multiplications. And in Power 11, we went ahead and introduced an external accelerator, right, that you can basically go ahead and put in your server, which allows you to be able to do things like fine tuning or large inference, not training, right? But you can actually do this, right, along with the CPUs that have your encode MMA, right? And this is very advantageous for enterprise systems because in enterprise systems you do not want to move your data away, right, from your server into something else and bring it back, right? So a nicely attached system which basically has an accelerator, shares the memory with the CPU, allows your data to be within your server and still be able to do a lot of AI inference and fine tuning. Okay, but this is not the only thing that you have to do, right? I mean, inference tasks need a lot of bandwidth, right? And any CPU that's even remotely targeting inference operations to be done on the platform need to support a lot of bandwidth. And this is just an example. I mean, it's not just IBM, everybody else has been doing it, right? But there's a significant amount of effort nowadays put on improving the amount of memory bandwidth, amount of memory capacity that you're putting in, because all these models are like huge, right, that you want to do inference on. And then, of course, coherency flows, right, because you have lots of cores, lots of in-core built accelerators, and they need to communicate with each other, right? And there is a lot of effort that needs to be put out there. Okay, and then I talked about enterprise servers, right? Where do we use these things for, right? So lots of very interesting tasks, right, that you can do on a CPU, on a server, right, with or without an accelerator card attached to it. And again, as I said, in enterprise, you don't want the data to go out because you're very sensitive about your data, right? So cyber resilience, for example, is a very nice example. So IBM with Power 11 has been touting about what we call a cyber vault, right? And cyber resilience is different from cyber security. So cyber resilience is, okay, now I've got an attack, how fast can I recover from that attack, right? So to be able to do that, you need to have copies available, copies that basically have been verified to be correct and that you should be able to restore them faster. And you can use a lot of machine learning to be able to do that, right? How to figure out copies, when to take the copies, right? And these are good enough compute tasks, right, that need AI, but they can be done on the CPU, and that's the kind of platform that is used for doing cyber resiliency. Fraud detection, right? This is again a very nice thing that's being done a lot on the CPUs, and again the reason is if you have a banking customer, if you have Visa or MasterCard trying to detect fraud detection on your credit cards, right? I mean, of course, they don't want your data to go out somewhere, right, when they're trying to do out there, right? So you want to do that detection within the server, right? And you can do this through machine learning instead of earlier checks, right? There used to be checks like earlier that, oh, okay, this person has logged in or has swiped his card in Siberia, so must be a fraud, right? I mean, he's living in India. Well, they may not be correct, right? Because you may be visiting Siberia, right? But there are other ways, right? If you actually deploy machine learning, you can reduce the amount of such false positives that you introduce with fraud detection. And this is a very nice use case for enterprise AI. Of course, these are not very compute intensive ones, right? So CPU becomes really good for them, but things like RAG is also very useful, right? If you actually have an accelerator card attached to your server, you can use that for offloading some of the high computation tasks for RAG and let the CPU do the orchestration around it, right? So again, your data doesn't go out of the servers, but you're actually able to do a lot of AI within the server. Okay, so with this, let me conclude. So as I said, we are in the AI era, right? But the general purpose CPU continues to evolve, and in different ways, right? Of course, there is a classic architecture improvements that keep happening for performance, for power, right? And that continues to drive. But on top of it, a lot of AI, right? I mean, the CPU, AI needs CPU because a lot of these tasks that we talked about can be done on the CPU. Of course, attached with and without accelerators depending on what application we're talking about. And then most importantly, AI is also helping us solve some of these very difficult problems, right? That are not so easy to solve with us, right? And including things like post-silicon tuning, which is what AI is actually enabling. So overall, it's a fun time to be, right? In the sense that, I mean, there's a lot of advancement that keeps happening in the CPUs, right? Along with what's happening around the world in AI, both driven by new workloads, as well as using new technologies to go build and design faster CPUs. With that, thank you so much.
Thank you, Jay. We finished well ahead of time, so
Sure.
plenty of time.
That's great talk. So I have many questions, but I'll stick to a few, or maybe one, right?
We'll come back to you again.
Yeah. So machine learning for microarchitecture, right? So let's say prefetching. Right? So recent literature where they use let's say neural network, LSTM, or whatever, right, for doing data prefetching. So they show numbers which are pretty good, but at the end of the day, we actually care insights more than numbers.
Correct.
Right? And so first of all, it shows that it's possible that we can push the limits, but it doesn't say why or how exactly we can push it if we don't use the limit models.
Correct.
Right? So is there a way where we can actually use ML to see the upper limit, but then again get some insights from there and then come back to the classical microarchitecture and revisit that so that you can push the limits using non-AI techniques?
So I think it's more, I mean, less a question, more a comment, right? In that sense, which is fantastic. I mean, right, just to rephrase, right? I think, I mean, this is exactly true, right? The problem with machine learning, using machine learning for solving some of these problems is you get numbers at the end of the day, but you do not know why the numbers came from, right? And there is always a risk when you don't understand why the numbers are coming from, would they actually hold? Right? Because most of these papers are run on simulations, which are shorter in time, don't represent the full application, right? And there's always a worry that, okay, I've got some performance, I don't understand why I've got this performance. When I take it to silicon, will I actually get the performance or not, right? Because there are so many other variables that come across there, right? So, I mean, I totally agree with what you're saying, this out here, that, I mean, these can potentially give us, some amount of headroom, right? Like, for example, there are certain applications which, okay, a lot of us think, oh, maybe there is no prefetching possible on these, right? Because there is no pattern that I can see, right? You put these things out there and then you suddenly start seeing performance. That basically drives, us to go and look into it a little bit more deeper and figure out what is the pattern that we've actually missed out so far and go and implement them. Right? So I completely agree with you. I think this is one great way of using AI to drive the motivation and pattern searching in certain areas where it's very, very hard for us to see the performance today. But I also believe that over time, the biggest problem with some of these approaches is they're also very costly to implement, right? And you're talking about CPUs that don't have area that much, right? You have to make sure you have to cram so much cores within a socket, right? So over time, these areas probably have to move towards being more efficient in terms of development. And maybe we're waiting for another AI algorithm to come out, which will end up being very, very efficient to go and implement it in the hardware, right? And be able to demonstrate the same thing that we're getting from LSTMs. So I would keep myself open towards all directions, right? As somebody building cores, I need performance at very, very little area to be added, right? And if these can deliver this, why not, right? But I think at this point of time, I also look at it more as something that's giving us a headroom that we can go after. So thank you for this comment.
Can I ask more? Or?
So do you actually come across a situation where the accelerator, the high accelerator, or the GPU is waiting for the CPU to complete some pre-processing tasks, for example, where this costly accelerator is sitting idle because the CPU can't catch up. So do you see much of that?
There is quite a lot, right? And depending again, right, like for the RAG use case that I talked about, right, where we basically have the spire and the cores very tightly working with each other. This ends up being a bottleneck, right? In many circumstances, there are also cases where we have tried to keep the memory common between the accelerators and the actual CPU, so that this can cut down this communication that happens, right? Instead of DMAing from one memory to the other. Right, so this continues to be a problem because CPUs are the ones which will do the pre-processing, the orchestrating, right? And I completely agree with you, Akaraj. There are scenarios that we've seen where this has been a problem, and it's not been an easy problem for us to solve, right? In most cases, we have just left performance on the table while doing that. Yeah.
Heartwarming to see CPU talk. Fantastic, absolutely remarkable, right? So, I'm curious. Do CPUs today implement some of these modern AI-based algorithms in the front-end pipeline, like cloud prediction and execution? Maybe I'm just out of the. We of course see a lot of this in paper, right? But in real hardware today, it's okay to say, you can't say, but if you can, I'm curious to understand.
No, so I think Biswa just talked about it. The problem with many of these is that, I mean, you can train them, right? You can probably put in the weights, right? But even just building the actual, for example, perceptron, right? That's still being used a lot, right? I mean, perceptron continues to be used, right? Now that's a very simple machine learning model, right? And we have the perceptron branch predictor in, I think many companies use that, right? And it's been a long time, right? Of course, Phage has been outperforming it for quite some time, so the focus has moved away, right? But there are places, right, where you could potentially use that, right? But again, right, it's all about how efficiently can you go ahead and build it, right? So, and that's where I feel today's use case is more towards tuning, and figuring it out, right? How can actually go ahead and tune some of these weights, right? So you build your prefetcher or you build your branch predictor with tons of different parameters, and then you can actually put an ML on it to figure out how to tune it. That's something that is definitely done by a lot of people, right? And that is very, very useful.
So that's offline, right? That's not on.
That's all offline, right? That's all offline, right? But you train it and then put it in, and which works for a certain class of workloads in a given server setting. That's where it's being more useful. Building it completely in hardware, I don't think that's. We probably need a little bit more research towards that, right? So.
Yeah.
Okay, good.
What would you say is the part of the CPU that has the most scope to improve?
Everything. I mean, everything. I mean, seriously speaking, right? I mean, because as I said, right, we struggle to deliver 15, 20, 25% performance, right? And if you look at it, right, I mean, if you look at any CPU that's coming out and when they're talking about different parts, what they have done, they will never say, oh, I just improved this portion of it and I've got like so much performance, right? They'll always say, I improved this, improved this, improved this, improved this, right? And depends on the workloads. And this is the beauty about classic, I mean, general purpose computing, right? There'll be certain workloads that will be limited by the front end, right? There'll be certain workloads that will be limited by how well you execute your loads. There'll be certain workloads that will only care about your caches, right? So every area matters, right? Because for a CPU, you don't want it to be focused towards one single workload. Otherwise, it's not a CPU; it's an accelerator.
Okay, so maybe the last question.
Thanks. So I think it's a comment, question, or data point, whatever way you want to take it, right? So I believe one way AI or ML can help microarchitecture community is, so this is the context. So we have, let's say, K microarchitecture ideas having M knobs, like, which means there are K cross M possible design choices. And we don't know which choice is the best for that given workload, right? But you can actually throw your AI and ML models, right, and get the best search space that you can get, right? Dynamically also, let's say, right? Let's say you use reinforcement learning and other stuff also. And then stick to one stable page once you understand what exactly is the system dynamics, right? Is that a way going forward, or this is too academic?
No, this is already happening with the software, right? Post-silicon stuff is exactly this, right? You're adapting on the fly to a given workload based on some amount of pre-learning that you've actually built.
But for microarchitecture, there are like tons of.
But when you're building, I think this is a great way, right, to go build stuff, right? Because when you're building, also you have a lot of choices to do, right? And eventually, at the end of the day, right? I mean, because you've got so many workloads, so many choices, people end up thinking of geometric means or whatever, one metric, and you basically go ahead and based on that, right? Or your customer will come and say, no, I really care about this workload, so you start tuning it towards that, right? I think this is a great way that microarchitecture has to evolve, right? Because AI can give you a very good way of figuring out how the different how the different bottlenecks, how the different trade-offs are there, right? And you can probably arrive at a much better point, right? Or build more configurability into your hardware to be able to do that post-silicon, right? So I agree with your comment. So.
Can I ask one more last?
Okay.
Okay, thanks.
So let me just make sure that maybe we should give it to, yeah. You can always talk to Jay.
My question is, as an architect who's designing for performance, like when your, let's say, primary goal is just pushing the IPC, how exactly do you think about the efficiency? Because, say, mostly, at least I work in performance modeling, so I don't see a picture of the efficiency right in front, right? So, how do you think about it? Like, do we design for a scenario where you're envisioning 100% utilization, or are there other more practical points that should be your default?
Yeah, so it's a very good problem, right? And since you talked about modeling, right, this is one of the biggest problems that architectural modeling people get into this, right? So how do you project from IPC that you're looking at, which is a simpler model, right? So it gives you more visibility when you're trying to solve versus looking at a whole system and figuring out how this IPC translates into overall performance. Is this the question, right?
That and efficiency as well.
Power efficiency you're talking about?
Because
right, performance per watt, right? So
I might be optimizing for, say, 100% utilization of a 100 core part, but that may not be the realistic use case, right? It might be say 50%.
Yeah, so it's again about, right, the advantage of looking at IPC as a metric and looking and focusing on performance, it becomes a point problem that you can actually optimize, right? But you need to look at the overall system as well, right? So as somebody, you said you work on performance, right? My recommendation would be just don't box yourself into just looking at this one IPC metric and doing around it, because eventually when you're looking at the overall system, everybody looks at performance per watt over a whole system, right? Throughput per watt or TCO, right? And it's very important, right, to be able to project that, right? So and keep an eye on that, because otherwise you'll probably end up thinking that you've actually made the system really good, and in the end the system will turn out to be not as good as you expected it to be. Right? So both of them have to go hand in hand.
With that we will once again thank you for presenting this momentum.
Thank you. Thanks.
We will now move to the last and most exciting talk of the session. This will be given by Subrata Mitra. He is a senior research scientist at Adobe Research. Initially, his research interest was more on distributed systems. Now it is more on machine learning and systems, computer systems. He has several publications in database conference as well as in machine learning conference. He got his degree from Purdue, PhD from Purdue, master's degree from University of Florida, and undergraduate degree from Jadavpur. Over to you.
Thank you so much for the kind introduction. So I am between you and the end of the day, but I thought that there is not enough LLM happening. It's good to see that it's ramping up, so I will take it to the final level. So I'm from Adobe, and so many of you already use a lot of Adobe products like Acrobat, AI assistants that's embedded in Acrobat, and then Photoshop has some assistant and Adobe Express, and there are other type of products which is more catered to the enterprise customers, which also Adobe is trying to integrate a lot of assistant to enable the customers to get rid of the setup cost or the consulting cost that was previously there to extract the data that flows into about their own customers and advertisement campaigns and things like that in an easily accessible manner. So, so from a distance, all this looks like there is some model which is actually doing the work. There's some simply calling some model, but actually in reality these are all compound systems, and there is lot of sub-components which is working together to make these sort of assistants or agents or whatever you call it active and useful for the customers. So what I will do is I will try to keep things at a high level to give an overall flavor of the problems that we are looking at. So at a high level, we are looking at sort of training-free optimization. Some people call it post-training optimizations, to find out how we can extract the most useful insight from this model with least amount of cost or latency that we have to pay. So here are like few design patterns that often come up in AI systems. So the previous talk talked about RAG, which is almost there in some form in almost all the AI systems. So RAG basically means that you extract some knowledge base, knowledge from some knowledge base, and then infuse that knowledge in the LLM to either override LLM's own internal knowledge by the knowledge base that you want to infuse, or augment the LLM to have more knowledge that might be required for either your product or the situation that you are dealing with. In context learning is some form of RAG, which I think Saurabh mentioned, where he was passing these examples to the LLM to create the compiler.
Remove the phone. Phone.
So compiled output. So in that case, the examples that you pass to LLM for LLM to teach how to behave in a new situation is an example of in-context learning. Attribution is basically whatever LLM produces, you would like to give back a user some assurance that that output is grounded in either the knowledge or the example or the facts that user would like to verify. So otherwise, LLM can sort of give garbage, hallucinations, made up output which is not very useful for real life use cases. So attribution is a way to guard that. And then of course there is certain amount of information that LLM can sort of digest to produce an output, which is often called context, although we are currently talking about long context model, which can take several millions of tokens of information in the model. But in reality, it doesn't work like that. So after a certain length, the quality of the output significantly deteriorates because models simply cannot sort of understand the context beyond certain limit. So how do you manage efficiently pack the information within the limit so that your output is very highly accurate and correct is the long context management. And caching and reuse is basically same as almost all part of the system. The more you cache, you can basically save like repeated computation, latency, and things like that. So I will have primarily two parts of my talk. At first, I will sort of focus on some aspects where I will go over this RAG in context learning and caching, and then next part, if I have time, I will go over the attribution. So RAG, as repeatedly mentioned, this is the sort of the very simplified pattern. So basically, some user sends a prompt, and then that prompt might have some associated information that is there in the knowledge base. And so just instead of just trying to get the answer from the LLM, we try to get the associated documents or whatever knowledge chunks from a database or knowledge base, and then infuse that in the LLM along with the question so that the response is more coherent. And then there are several situations this appears, sort of if you want to, user wants to know how a product works, and there are documentations of the product, maybe latest documentation versus previous documentation. Instead of LLM answering from some previous version of the documentation, we want to infuse the latest documentation to make sure that LLM answer is sort of grounded in the latest documentation. And then of course in code generation, we might infuse the definition of several functions when it is trying to generate the code, so that it knows how to optimize the function calls for those codes, keeping in mind how the definitions are. So all of these things are very, very repeated pattern that often almost in all the assistant or agents that we build. As I said, ICL is a very close sort of replica of this. Instead of knowledge base, when people try to add examples with the question, then it becomes like in context learning, and often these examples can basically bubble up. You can have like a laundry list of examples, but not all those examples are relevant in every scenario. So in that case, basically depending on the question, dynamically some most relevant examples are selected and then infused in the LLM to make it produce the answer, which is basically one version of dynamic example selection, which is exactly like the RAG. In Adobe's case, we try to answer a lot of product knowledge, product information. This is basically the data that is stored about the customers, and customers are asking very high-level business questions like how my business is doing. So LLM has to understand first is what this high-level question means, and then decompose into some sub-questions which can be then grounded back in the data that they have about the customer. So in that case, this natural language is transformed into SQL, and then often these the way that this transformation should happen is not trivial. So a lot of these very specific examples has to be passed to the LLM to produce a correct SQL, schema names and columns and things like that, and to produce a faithful SQL which can be then run against a database, get the numerical answers, and then infuse this in the response to get to the customer. So these are some examples. Now I will just briefly go over. I mean, probably everyone knows how LLMs work, but just a little bit of more granular information. So LLM, as we know, is auto-regressive generation. You pass some, a sequence of tokens. It produces the next token, and then that goes into the LLM, and it produces the next token. So primarily, it has like two phases, which is one is called prefill, where basically if you pass like a sequence of knowledge, it calculates something, the relationship between these tokens, which is called attention calculation, which happens in a prefill stage. Here, the LLMs can see all the sort of, if we say tokens, we can sort of simplify it as words or something similar. So it can see all the words, so it can calculate all these calculations, how which word is related to which other word in a sort of parallel fashion, which is prefill, which is typically compute bound. And then there is a decode or generation phase where basically based on this understanding, LLM produces the next output token, which is called decode token. This is the auto-regressive part, which is typically memory bound. So so now when we are further calculating the attention on this newly produced token to produce a new token, which comes once upon a time there, which is supposed to be the new token, we don't need to calculate all these attentions or how they sort of relate to each other again, because how once upon a time once upon a was sort of the relation between those was sort of computed is already there with us. So we can just take advantage of those pre-computed calculations and then just focus on the new computation, which is with respect to time, and then calculate the incremental difference. So which is basically the caching that is used during decode phase to to make the decode faster. This is just some visual I got, really nice, interesting in Google, someone made. So basically, this is the classic transformer paper, which has this sort of transformer diagram. Once the prompt comes, it is typically divided into three vectors: value, key, and query. And then some calculation happens between this value, key, and query, which is the essence of the attention calculation, which produces this relation, which is like initially it produces like a giant n cross n sort of attention matrix on which some maximal information is extracted and multiplied with a value vector to get the final understanding of what is the most important context for this new query, which is the Q. And if you do it naively, you can see that it's a n cross n computation for every new Q query. But the caching that is used is basically, which is shown in the down part, is basically you can basically cache all these sort of violet rectangles, which is from the previous step, and you don't need to calculate them again and again, which is embedded and speeds up the decode process. Now this thing, which is called KV caching, greatly speeds up the decoding, but it doesn't help in the prefill, because in prefill there is no need for caching, or caching cannot be utilized because everything is present at one go, so it doesn't really help. So when we looked at the AI assistant that we were dealing with, we basically sort of found some interesting patterns. First of all, unlike ChatGPT or Gemini, these AI assistants do not produce lot of verbose answers. So they produce an answer which is with respect to the question that they are asked and the knowledge that they were given. So it is often that the input that goes into these models are much, much larger than the output tokens they produce, because it probably produces some simple number or some answer which is very direct to the relevant to the question, but the information that goes into its input is basically a lot of documents, maybe a lot of sort of examples and things like that, which is basically consume a lot of tokens. So actually, if we look at few example scenarios where these assistants were made, and if we sort of see what fraction of the input tokens correspond to different parts of information, we can see that there are a lot of tokens that are consumed by RAG chunks. Then there are some mother prompt which basically says you are an awesome agent, blah blah blah, and then some examples, and then at the end some question, and then there will be some output that the model produces. And as I mentioned, prefill is very, very compute bottleneck by compute. So if you want to basically run the system at scale where a lot of this long context processing has to happen, and if you try to batch them, then basically the latency of this prefill time shoots up. So, so what we try to look at is how can we reduce this prefill time by clever way of caching and reuse. So, so this is the view of sort of the layer-wise view, what happens inside the LLM, basically what I said in terms of this block diagram. So these documents go into the LLM. You can think about every such, these documents have, we can call it chunks, has a bunch of tokens. So document 1 has some tokens, sequence of tokens, document 2 has some sequence tokens. These are getting sort of computed across the layers, and at the end the answer is being produced. And so if we look at the basically the distribution or the popularity of these chunks, it's a heavy tail distribution. So there are very small number of very popular chunks or documents which are being answered on repeatedly. So the idea is very simple. How can we reuse these computation that was done with respect to these sort of documents so that we do not have to prefill them again and again and therefore save the computation. So now we cannot just simply use their cache that was computed in the previous time they were used and reuse them in the new situation, because how the attentions are calculated is basically they have a causal and sequential relationship between them, which is very important in producing the outputs. So if we violate this sequence or randomly try to sort of bring or mix up these tokens, then the quality of the answer gets degraded very fast. So on the right, you can see that basically this is a simple experiment on the blue line, for example. If we just take a cache of a chunk and then just try to reuse them in new situations, as the number of chunks that are needed to go into the RAG increases. So for example, if only one chunk is used all the time, then there is no problem. We can, basically it was used in the same context, same prefix all the time, so its cache basically may not change. But once it starts, that combination of 2, combination of 3 starts to appear, the degradation of the quality, Rouge F1 is a sort of, you can think about it as the accuracy, that starts to degrade. And on the left plot, we show that the same thing basically. So basically, if we actually looked at the sequence in which they appeared, and if we say that, of course, if it's a one chunk, then we can reuse them significantly large number of times, which is basically the frequency. But as the prefix length increases, the combination becomes rarer and rarer. So therefore, the scope of reusing them in the same exact sequence becomes lower and lower. So therefore, we need to find how to reuse the previously computed chunks in a new situation so that the quality does not degrade. So so basically, what we found out that if you take this as a sequence of tokens, if we look at how the attentions are calculated, so if there is an example here, there are like 8 tokens. if we take the attention calculation between these tokens, we can see that there are some attentions that are being calculated within the boundary of the token, and then there are some attentions that are being calculated across the boundary of the tokens. So if we can find out that how strong is the attention or the relation of one chunk within its own boundary compared to the attention with across the boundary, or how dependent this chunk is on other chunks versus how it is dependent on itself, we can get a pretty good score of the reusability of these chunks across different scenarios. So this is exactly what we do to build a system. I will show more examples here. For here, you can see that there are two examples. So C2 is a chunk which was cached with a completely unrelated chunk C0, and then some question was asked on it in a new situation. So the system could answer this question very accurately, because in this case C2 was self-dependent, so it is self-contained. So we can see this if we plot the distribution of the attention basically side by side. This blue one is intra-attention, the attention within itself, and inter is the attention across its own boundary. You can see they are sort of separated, and they will most likely, this one will be on the blue one will be on the right, and the orange one, inter, will be on the left, because how LLM calculates its attention is they give huge importance to the position. So the closer the tokens, the more the attention, and the farther the tokens, the less is the attention. So here is another situation which basically is a completely different scenario. So C2 was cached when it was heavily contextualized with a chunk which had relevance to it. So you can basically, if you read, you can see that the topic that C1 and C2 talks about are very relevant. So it is visible if we plot this again, the distribution of the attentions. You can see that they have a huge overlap. So they are basically intermingled with each other in terms of the distribution. And the result of this is also evident if we now use this cache, which is sort of corrupted by C1, and try to use it in a new situation and answer the same question. The answer will be wrong, because now C2 is not enough contextualized with the new situation. So with this insight, we basically build a system where we can basically mark these caches that we have created in the previous situation and say that if the distributions are separate enough, then this is a good cache to use. So we can directly use them, and if they are overlapped with each other, then they are bad cache. We should not use them. We should recompute them again. Many often the real life situation is not this or that; it's a mixed. So there are some partial overlap. So in that case, we can actually identify exactly which are the tokens in the data chunk which attended to significantly to the previous tokens, and just partially recompute them, and then get a good quality answer. So this is the design of our system that we built for this RAG, which was published in Sigmod. And we can see that, I will not go into this. So basically the accuracy, if you see sort of how much quality we can preserve with respect to a lot of competitors. So because of this recomputation and this way of determining cache good and bad, the quality is pretty good. And then the main benefit comes in the reduction of latency that we can provide with respect to, of course, with respect to full recompute is significant, but also several other methods which do not have this intelligence. So with this, I will just go over very quickly with some interesting observations which relates to attribution. So again, attribution, as I said, this is the answer, this is the question, this is the context. Attribution problem is identify in the context which part of the answer actually it came from. And I again mentioned these two distributions. We can calculate a distribution which is the green part within the context, and then within the answer and the answer to context. And when we look at this for a model across all heads and all layers, something interesting that we found out. We found out that even if they are related to each other, there are only few heads where they have a significant overlap, and there are large number of heads where they are not significantly overlapping. This is for a situation where they have they are supposed to have a significant relationship, but still out of, there are probably 1,000 heads here. Out of those 1,000 heads, there are very few heads where they actually are overlapping. Now for attribution, overlapping is good. Overlapping means that they are related and we can find out if they are related. So basically there is another observation that the way this attention calculation or stack works is there is a softmax. Softmax is basically this function which basically sharpens the distribution. So if we see that the distribution before softmax and after softmax, we'll be able to see that this clear signal that was present before we take a softmax vanishes as we apply the softmax, because everything looks very sharp, and then there is of course nothing that we can distinguish from that post softmax sort of graph. So this is a paper that we sort of wrote around this observation that there is a statistical framework that we can build to identify what are the heads that are important for attribution, and there is another task which is basically called KV compression or KV eviction, where we basically try to get rid of a lot of irrelevant tokens from the context. So that can be identified easily if we build a statistical framework. This is basically again the same story that what I mentioned verbally, that I forgot to label the LLMs. One is a llama and one is a Quen model. So this is the sort of all the heads across layers, and these are the overlap area. So you can see there is a very small number of layer comma head where the overlap is high, and then it's a long tail distribution. Actually, if we perform some more experiments, that if we consider this small set of heads and keep on adding one head at a time in the sorted order of their overlap area means relevance, the quality sort of increases slightly. But if we try to add irrelevant heads in the picture, then the quality degrades sort of drastically. It's not so visible for llama, but it's visible for Quen. So this basically means that there is a noise these additional heads inject in the task, and if we can discard this noise, we can get a very pristine understanding of attribution from this. So I'll not go over this. We have a very nice way to calculate this overlap without going into computationally expensive methods. But I guess this is the main result, is that actually with that kind of understanding, if we do the attribution, we can actually, like a very small model, for example, llama 3.23b or maybe Quen 8b, can perform better than GPT-4, because we could completely distill the noise from the system and then find out where exactly the model is looking at to find a very good quality attribution. And this is for the compression task. I will skip that. More interesting part is we can apply the exact same technique on images. So here is an image of some dog, AI generated image, some caption. Now if we focus on this reading a book, so we can see that the model could attribute this reading a book to not only the book but also the glasses or eyes of the dog. So model can attribute very abstract concepts through the same method. So I think with this, I will, how we are doing with the time?
We have 5 more minutes.
Okay, so the main advantage of this is that because we are only dealing with very small number of heads and a very small model, we can have very fast attribution, which is not possible if we are calling some huge model to perform the attribution. So this is the main benefit, that we can get very fast attribution but high quality attribution through this technique. I will just maybe not go into detail, but this is a line of series of work that we have been doing from last year, where we actually first tried to look at how this sort of caching of intermediate steps can aid in text-to-image generation, where we observe that this denoising steps in the text-to-image generation takes huge amount of time, and if we can cut these denoising steps by injecting previously compute latent steps in the text-to-image generation, we can completely reduce the latency significantly. So this is a line of work that we did. I will probably not go into the details of this one, but I think these are some of the examples which are very encouraging. Is that we could take a if we could take a noise that was generated for a very different subject but had some similarity with the new image or prompt that was given to the system. But we could transform these sort of latent noises at a very advanced stage to a new sort of image by cutting significant amount of computation that is needed. Yeah, so this is our NSDI 2024 paper. If you are interested, you can read this approximate caching. So with this, I will conclude. This is our sort of intern time. So this is a picture of our team with almost 60 interns. And if you want to find out more about the research or our group, you can go to that. And we are currently hiring for PhD interns for the next summer.
So you talked about this attribution and similarities in thread and things like that. Do you also use it for doing pruning of the network, or you do it only for KV cache compression?
We have
does
not
it
yet
make
tried.
sense to, first of all,
Yes,
does it
yes.
make sense to talk about pruning?
Yes. So we have not yet touched anything internal to the model. So the idea is, for now, our agenda is not to touch the model and create a framework around these open source models that are coming up, so that we can quickly move from one model to the other model as the model improves, and not get stuck on either fine tuning or doing something substantial for a particular model. But that is definitely like something that we try to explore, but not deeply, is how we can shrink the model and get rid of. So some things that we did is layer skipping.
Okay.
Layer skipping meaning, for the same kind of analysis, not every prompt has to go through all 32 layers. Depending on the context, we can try to basically skip some of the layers in between. So that is kind of pruning, but dynamic pruning. So not like getting rid of them completely. We are basically getting rid of them for the context of the prompt. Yeah, but that's a great point that can be done. Yeah.
We see anybody else ready?
So the work that you showed with sensitivity heads evaluation with the Gwen model, is that published somewhere?
It's currently on archive.
Okay.
Yeah. So this is the RC stat is the name. So I had, yeah, that is the.
Thanks.
Okay. There are no further questions left. I think Arka will take over now.
Yeah. So I know all of you are tired and probably sleepy. There is a high tea outside. I'll not take more than few minutes. First of all, I want to thank you all, participants, speakers, the session chairs. That whoever I reached out to, they always said yes. So thanks a lot for that.
Well, thank the organizer, Arca.
Thank you. Now, that is the interesting thing. So, I have never done this kind of organization, okay? And I'm very afraid of that because I'm not good at that. So, what I did is that when this came to me, I was a bit afraid. So, I actually, sought the help of our serial workshop organizer. So, he organizes Sumit. Thanks a lot, Sumit. Without you, this would not happen. So, if those who don't know, Sumit organizes system workshop every year. One is there in a month, right, from now. So he has still an energy to organize another workshop, right? And even then, he said yes to me. And then he brought Manoj. Manoj helped out from the start. Particularly, I have a habit of forgetting things that I would not actually do, and he will keep reminding me in WhatsApp. Thanks a lot, Manoj. Of course, our sponsors, without whom it was not possible to organize an event. So we have Adobe, AMD, Google, Microsoft, and Nutanix. And then, of course, our all the volunteers, right? First of all, I would say the head volunteers, Ajay. So he before I really put him under the bus and said, okay, I need help. He was writing an IISc paper. The submission is in a couple of weeks, and last probably a few days, probably a week or more, he completely stopped that because of this. And then there's Shweta, Abhishek, Rajeshwaran, Dhananjay, Amit, Huzam, Minakshi, Anuparna, Ayman, Sayak, Rahul, Yatharth, Pratik, Kaushik, and of course the Neha. Apart from that, Nishita and the CSA office, Akshaynath is here all the time, and Sanjay. Okay.
All the volunteers.
So, and last but not the least, beyond this workshop, I have someone to thank, and I want to thank Professor Govindarajan. So essentially, in my mind, so his contribution goes far. This is not just a workshop, right? So he is one of the first person who kind of I look up to you as started the computer architecture research that is visible outside from India. So we are all here because you started it. So thanks a lot. And as a as a small appreciation of that, like Mark, if you can do the honor.
I didn't know this come.
Of course, that was the plan. So
You be there.
yeah.
No, it should be on the other side, Arka.
Oh. Why?
Thanks a lot. This means a lot to me. Getting it from you is all the more interesting, and getting it from Mark is even. I think the case. Thank you.
And you don't have to put it in your carry-on bag.
Of course, we quality.